start a new chapter, Mechanical Properties of Materials. I just made an announcement for midterm, so if you can check the canvas. The midterm will be on 26 March, the Tuesday, during the lecture, 15 minutes, closed book. I also have some introduction, you can check that on Canvas. And mechanical property will be included in the exam content. Okay, so probably some of you or many of you already did the experiments in the lab, right? So in the experiment, we measure 3 or 4 important mechanical properties of the material. We measure the force displacement curve, like what we've shown here. Okay, so in this chapter, we will introduce different important points on the stress and strain curve. Maybe we will not use force displacement curve, we'll use stress and strain curve and introduce what is the stress, what is the strain. I believe many of you parallelly are taking solid mechanics 1. So in solid mechanics 1, I believe you already know what stress is, right? What strain is, relative deformation. And here we focus more on the mechanical property side. Okay, we're not going to solve like the beam problem, bending problem, twist problem. We're not going to solve that kind of problem. But you need to have a physical sense what kind of deformation modes you will get for different loading condition. And in that case, what kind of deformation the material will respond to the loading conditions. And most importantly is that you need to understand the physical interpretation of different points here on the stress and strain curve. So that's the key point of this chapter, okay? And also you need to distinguish different properties, like distinguish the elastic property and plastic property, and what is the key importance between elasticity and plasticity. And also you need to understand what tensile test can measure, what kind of mechanical properties a tensile test can measure, okay? And what kind of properties a hardness test can measure. Okay, so here, introduction, I have some animation here. So one side is like a specimen. This is a metallic specimen and gripped on 2 ends, and we are going to apply a tensile loading, uniaxial tensile loading like what you did in the lab. Instead of just look at the stress and the strain, we actually have another technology to look at the localized deformation, means at different position, the deformation may be not homogeneous, maybe not a constant, maybe different from the other location. How do we characterize that? We set up a camera, and while it loading up, we have some like spray, and then this spray will have this kind of random dispersed particle here. Okay, that's some ink, you know. We call it speckle pattern. And then as you can see, if we load it up, this kind of speckle pattern will get like further away or like stretched, deformed, right? And then through certain technology called digital image correlation, maybe in your graduate school you will actually do that experiment, but it's not required here. You just need to know that, okay, there's this kind of technology called digital image correlation. Okay, so this is a technology can see localized deformation, means we can see the deformation at one position relative to the other position, not overall. Actually, what you measure is the overall deformation. It's the overall elongation in the end of the day. And this technology tells us like what's the localized deformation. So here, obviously, first deform, right? The color contrast, the lighter means deform more, okay? And here is still not deform so much, and here deform more. And then as it elongates, you can see here has like a stress concentration, strain concentration, and break. Okay, near the fracture surface or fracture interface, you'll see there's like a maximum stress or maximum deformation occur there that causes the fracture here. So this is the formal way to characterize the mechanical property. And in your daily life, actually, the mechanics and the elasticity always exist. And that exists as what? As energy, actually. Okay, so I just download a very funny animation that, so this bunny like works so hard to create a huge tensile force in this ribbon. And this ribbon is very, very elastic. And once the bunny accumulates enough energy, and then there's the energy conversion from the elastic energy to kinetic energy, and it just bounces away, and even further away from this turtle. Okay, this is like bunny turtle. This is the new version, the mechanics version of bunny turtle competition. Okay, so bunny is smart, and the turtle is very diligent. Okay, turtle always like continuously, paddling at a constant speed. But the bunny just, try to accumulate enough energy and eject it at once. Okay. Anyway, so in this chapter, we are going to look at two important quantities and their relationships, stress and strain. And the stress, how to achieve stress. In your solid mechanics 1, how do you achieve stress? You achieve stress by force balance, like not just in your solid mechanics 1, maybe in your fluid mechanics, right? So if you want to analyze a finite volume of a piece of fluids, you also use the force balance, but different types of force balance, okay? And then if you achieve that, then force per area give you pressure in the fluid dynamics, and the force per area for a uniaxial bar. If you do like tensile force, that is the stress derived in your solid mechanics. Actually, solid mechanics, fluid mechanics, they somehow merged. They are all under the envelope of the mechanics, right? So how do we achieve the relation between stress and strain? So if this is an elastic material like the ribbon, here we use elasticity relation, and that is the very popular law, actually. We call it constitutive law. Constitutive law is a law to tell how the material responds to the external loading condition. Okay, so one of such kind of constitutive law, we call it the elasticity relation between stress and strain. And this is the most popular relation that used in engineering, especially for metals. So we know that metals is one of the most important engineering materials. And one of the most important mechanical constitutive relation is the elasticity relation for metals. Okay, so here we will also introduce what the elasticity relation is and what kind of component from strain and what kind of component of stress is linked by this elasticity relation. And what do we understand about the strain? We understand strain as the kinematic relation. Maybe you don't quite understand the word kinematic, what kinematic means. Kinematic means geometric relation. So it's like if you studying like the balance of a bar, right? If you study a force balance of a bar, and this bar is not like one-dimensional. Maybe it has some cross-sectional area. So this cross-sectional area could be rectangle, could be a circle. Maybe it could be some other weird shape. It will have the moment of inertia. And the moment of inertia is the integral of the density over the whole area, right? Give you expression, and you have that formula. You can look up that formula. And then with that, you can calculate the bending moment and something like shear force, so forth and so on. So this kind of calculation relates to relative shape change. Or more general statement would be relative geometry, geometric change. Okay, relative geometric change. The whole thing actually tell you the strain. Okay, if you can calculate the relative cross-sectional area change before and after deformation, you'll get in-plane strain. If you calculate the relative length change of a bar before and after deformation, you'll get axial strain, right? So strain is nothing but the calculation of relative geometric change. Relative is very important. You should calculate two states. One state is the deformed states, and the other state is the undeformed states. And then the difference between these two states is the strain. So sometimes you'll find strain doesn't have any unit because it's a relative quantity, okay? So here we summarize the types of loadings for a solid, and I use a very simplified geometry, which is a beam. Okay, it's a finite geometric shape beam. Okay, then it's fixed here, and we set our coordinate system. This is very simple to all of you guys. We have the shear force in this direction in purple, and we have red color, that's the normal force, right? And here I just use compression. If in the other way is the tension, and we have M here in maroon color is the moment. Okay, so the moment gives the bending, and shear gives you the change in angle, right? And normal force gives the change in length. Okay. And here is the link between mechanics and materials. So if you just look at a tiny little bit of the material here, atomistically, materials like atom is stacked periodically in 3 dimensions, and this is the part not discussed in solid mechanics. In solid mechanics, we only look at the force balance here, right? We only calculate the stress state, right? Here in material, we really need to look at the material at a small scale. So at a small scale, it is actually the deformation or separation between atoms happen if the material as a whole suffers some additional loadings, okay? And okay, I made an animation. Maybe in your lecture notes you cannot see this animation. Anyway, I made an animation here. So in chapter 2, when we discussed the interatomic potential, remember, this is the interatomic potential, and this is the potential function, right? And if we find a force vanish position that corresponds to the equilibrium position, so the equilibrium position gives the energy well here. Okay, that corresponds to the separation probably here. That's the equilibrium. So that's the separation of atoms that form this kind of 3-dimensional periodic structure. And now if we pull it or compress it, okay, we will change, right? We will change the separation. And if such a change is small enough, means this atom just, hop from left to right, right? Cannot escape from the energy well, then this material still maintain its integrity. And if we remove all the force, it will go back to the equilibrium one day. If the force is too big that the atom escape, then it completely separate. So actually this is the linkage from atomistic point of view or from crystal point of view, how a material fracture. And from this chapter, and in next chapter, maybe throughout the rest of the content of this lecture, we will discuss how the material as a crystal structure will fracture or like plastically deform, cannot come back to its equilibrium position anymore, and what condition is that. Okay. So if we have normal force like the red kind of force, in your mind, you have to have this kind of mapping, okay? That maps the pure stretch and pure compression. That's change in length, right? That's the change in length. I think your solid mechanics instructor will tell you normal stretch change in length. That corresponds to the red force here. And if you have the purple force, right? That's V, we call it shear force. Okay? The shear force gives you change in angle. So that's why I say, what is strain? Strain is a kinematic relation, right? So strain is a relative change of the geometric, is a relative geometric change, okay? So it's a relative geometric change. So here correspond to different types of force. It has different types of change. The normal force gives you change in length. The shear force gives you change in angle. How about moment? Moment give you all. Moment give you this kind of thing. So if you have a bar here, and then if you apply the moment like this, can you imagine how it deform? It deform like this, right? Deform like this, and then you have a central line that not extend or contract, and all the particles here, they're all stretched. Okay, and all the particles here, they're all compressed. Right? So I believe, and also if you draw a line here and here, so it also has like change in angle before and after if you compare this one, right?